Hello all, a warm welcome to all of you. I'm Kishan Joshi, the chair of Power Electronics Society San Francisco Bay Area chapter, and it gives me great pleasure bringing more power to 2022 with this webinar. A little bit of history about our chapter. We were the recipients of the 2017 Santa Clara Valley and Region 6 Outstanding Chapter Awards and the 2017 Pell's Best Chapter Award. Today's talk is on high power density, high efficiency, altitude ready solid state circuit breaker for hybrid electric propulsion by Dr. D. Zhang, associate professor at Naval Postgraduate School. We look forward to an exciting talk. Thank you, Dr. Zhang. I would like to thank our IEEE co-sponsors for their support, the Santa Clara Valley PES IAS chapter, the Pell's Milwaukee chapter, the Santa Clara Valley Reliability chapter, PI Square Austin chapter, the Santa Clara Valley PSCS chapter, and the Oregon PES chapter. None of this would have been possible without the support from the excellent team of officers and volunteers from the Pell's San Francisco Bay Area chapter. And I would like to thank each one of them for their support. Okay, so IEEE senior membership is the highest grade one can apply through either a self-nomination or being nominated by others. There are a number of benefits like recognition, leadership, eligibility, and others listed here. We can help you with getting the required recommendation, so please feel free to reach out to us. Do not forget to check out our website for info about current and past talks. The slides and videos for a number of talks can be found in the archive section. We'll also be uploading the PDF slides and the recording for this webinar in the archive section. So please feel free to go there and check it out after the presentation. We'll send an email once we upload it to all the attendees. Also, do follow us on Twitter at sfbc_Pels. Before going ahead, I would like to also mention about our next talk on powering the EV revolution by Dr. Maurizio Di Paolo Emilio, who is the editor-in-chief of Power Electronic News on April 21st, 2022, from 10 to 11 a.m. PDT. Please feel free to register using the link shown here. Following is a list of events planned for the year ahead on a wide range of topics related to power electronics. This is just a teaser of all the events to come, so please follow us on our website or on Twitter or LinkedIn for more information on these coming talks. If you'd like to be in loop on all the great talks, events happening, then IEEE eGrid delivers all that info down to your inbox for free twice a month. Be sure to register at the link shown, which is egrid.biz. Finally, thank you for being here. Before we move ahead, a little bit about our speaker today. Dr. D. Zhang received his Ph.D. from Virginia Tech in 2010. Since then, he worked in electrical power and energy areas in General Electric Global Research Center for 10 years, until he joined NPS as an associate professor. His current research focuses on power system and power converter technology in Navy applications, especially related to medium voltage DC system. He received 35 US patents, published 22 IEEE journal papers, and served as a principal investigator of 6 projects with about $20 million of funding from NASA, ONR, DOE, and NSF. Now, I would like to hand over the control to Dr. D. Zhang for the exciting talk. Thank you, Dr. Zhang. You can take the control of the presentation.
Thank you, Kishan. Hello, everyone. It's very exciting to have this opportunity to present the team's work on the fast, lightweight, altitude ready solid state circuit breakers for hybrid electric propulsion. So this is a project sponsored by NASA, and the NPS is collaborating with Virginia Tech, University of Connecticut, and Clemson universities, and also NSWC folks to deliver this. So this is a 3-year project. So we are kind of halfway through it. So I will just give you an update on what we have achieved so far. So first, I will talk about the application background and some specifications we received from NASA. Then after that, I will give the explain the technical solutions we come out to meet the very challenging technical metrics. And in the end, we'll show the prototype design and test results. So high-related propulsions is a new applications to reduce the carbon emissions and increase aircraft functionalities. So there are many architectures, right? This is just one example proposed by NASA. They call the star cable configuration. You can see the basic idea is to add a tail cone fan as the back of the aircraft, so we can recover some of the energies stored in the boundary layers along the fuselage. Okay. To achieve these ideas, then we need to deliver powers, right? Attract powers about 2 megawatts from the engines and delivered through the electric cables and use that to drive the electric motors. And since we need to deliver or transmit like megawatt powers over long distance, and as we know, the weight is critical for aviation applications. So we picked the medium voltage DC as a system. But then, as well known, we need a solid state circuit breakers, right, that can clear the fault in the medium voltage systems, right, if there's a ground fault. So this circuit breakers is a key enabler for this concept. So this is the key specifications we received from NASA. The system inductance is about 0 to 50 microhenry. It depends on the fault locations and also the locations of the solid state circuit breaker. And it should be a generic solid state circuit breaker, which means can block bipolar voltage and carry bidirectional current. There's no need for gigavolt isolation at break levels, and should be PD-free higher than 35,000 feet. And the rated voltage of the system is about 2 kilovolts and rated current about 1,000 amps. The torque efficiency is 99.5%, and the density is higher than 100 kilowatt per kilogram, or the total weight must be less than 24 kilograms, or 53 pounds. Right? And per second speed is 10 to 500 microsecond, and there's also some cooling requirement. So one thing I want to emphasize is solid state circuit breakers need to be installed in both DC buses, right? Because this is critical systems. So the system must continue operating with a single point ground fault, just like this, right? So if you have a single point ground fault, so one pole is 0 volts and the other pole will become like 2,000 volts, right? So if we have the solid state circuit breakers instead in both DC buses, and a system running with a single point ground fault already, and if the second ground fault happened, and the 2 ground faults actually can bypass one solid state circuit breakers. So if we have both breakers, then the breakers that is not bypassed can be turned off to clear the fault, right? Just like this. Of course, after fault is cleared, if the short circuit fault is still there, then these breakers need to withstand the full DC link voltages, 2 kilovolts in this case, like plus and minus, right? Depends on the location. So each solid state breakers must be able to clear the fault by itself and block plus minus 2 kilovolts. This is the worst case for the design. So in the designs, we only design the solid state circuit breakers can handle the fault by itself. And later on, if we have both that work together to clear the fault, it's only easier. Right? And that also means the total weight of the 2 solid state breakers is less than 24 kilograms, or each one of them must be less than 12 kilograms. And the total losses is 0.5%. Okay, just keep that in mind. So before we talk about the proposed solutions from the teams, let's have a quick review of the operation principles of classic solid state circuit breakers. So this is a single line diagrams of a medium voltage DC system, right? It has a medium voltage DC source, has a solid state circuit breakers, has 9 inductance, and also has a load. The solid state circuit breakers, actually the structure-wise is quite simple. It has 2 components. One is semiconductor devices that can block bipolar voltage and carry bidirectional currents. And also has a component that can absorb the energy, right, in the systems. Typically it's e-MOV. So in normal operations, the devices are turned on to carry the current, right? The load current will just flow through the solid state semiconductor devices, and the voltage across the solid state circuit breaker is almost 0, right? At this point, its fault occur. And then, because the node had been bypassed, then the DC bus voltages will all across these 9 inductors. Of course, the current will increase rapidly. So once the current exceeds certain threshold levels, right, ITH, the fault has been detected. But it will take a while, like some depends on the response times in the systems. After the current will keep increasing until after the delays of the response times, the devices will be turned off. Right? Once the device is turned off, the IGBT current will reduce to 0, and the system current will be commutated to the MOV branches. Right? The MOV will pick up the current. The MOV is kind of a resistance. Once the current flows through the MOV, the MOV will generate a high voltage. Right? We say it's clamping voltages, and these voltages is higher than the system dispatch voltages. So you get elective voltages across the line inductance to starting to drive the fault current down. Right? And during this process, as you can see, the MOV is withstanding high voltage and also carry high current. Right? So during this stage, clamping stage, MOV is absorbing energies. So after the fault current, a system current is reduced to 0, right? The fault is cleared, right? Then both the devices and also the MOV will be in standby mode, and we need to withstand the full DC voltages, right? That's the basic operating principles, okay? And the peak current here, you can see the peak current here pretty much can be estimated as the ITH threshold current plus the DIDT, VDC over I, times the response delay. So then what is the design constraints for the 36 circuit breakers? The key design constraints is, under no condition, you want to make sure the semiconductor devices can withstand the transient voltages. As you can see, once we turn off the devices, right, you will see there is a peak voltages here across the 36 circuit breakers. And the peak voltages can be estimated as the clamping voltages or the voltage across MOV, where MOV carries a high current, a peak current, plus the LDIDT, the transient voltages, right, applied to the parasitic commutation loop inductance. Right? This is a parasitic inductance, right, between the MOVs and also the IGBT. And since we are commutating the current from the IGBT to the MOV, you will see a high DIDT. And once you are trying to push a high DIDT through inductors, you will see a voltage, right? So these two add together equal to the peak voltages. And these voltages must be below the semiconductor device's maximum voltage rating. Otherwise, the device will be damaged almost instantaneously. So this is a key design constraint. And also, we see that MOV will absorb energies, right? And MOV, of course, has a limited capability to absorb energies. So the energies absorbed in MOV can be estimated in these equations, right? We'll not go to the details, you can find some references, but pretty much is proportional to the energies stored in the line inductance, right? At peak current, right? Proportional to that. We want to make sure this MOV can handle this. Luckily for this design, since the system inductance is less than 50 microhenry, so if the peak current, right, is limited to about 4 kiloamp, then I will see how we do it. Then MOV energies is only 300 joule each for 2 poles, right? If both of them can work together, or it was about 1400 joule, right, for a single pole. This is the worst case. This can be met easily with the single commercial off-the-shelf MOVs, right, typically higher than 3 kilojoule. Another thing is, after fault is cleared by the breakers, then MOV in the worst case will need to block the full DC link voltages. Right? These are resistors. When you see a voltage across it, you will see a leakage current flowing through it. So even the MOV can temporarily absorb a lot of energies, right? A few kilojoule. However, it has a very poor or limited heat dissipation capability, typically less than 1 watt. Right? So as continuous blocking voltages, the leakage current must be only in the range of like 0.1 milliamp, right? Because you are blocking 2 kilovolts. So in the solid-state circuit breakers, the MOV is continuous blocking voltage rating. You can find it from the MOV's datasheet. Must be higher than the system DC link voltages. Right? VDC must be less than the VMOV continuous voltage. So as you can see, most of the design constraints are around MOV. Right? So if we can find MOV, for example, can block 2 kilovolts continuously, and also can clamp the voltages at fairly low, like 2.5 kilovolts, right, at 1,000 of amps, the job is done. It will be easy. However, the MOV's performance is not that ideal. Right? This is just examples of VI curves of a series of MOVs. This is from interviews, but if you check the product from other vendors, they all have a similar performance. Right? So this is VI curves, but it's a log scale, right? This is voltage in log scale and also the current in log scale. So within a certain range, it can be approximated with like a linear relationship, right? So we can define this kind of similar to the Ohm's laws. We can define kind of a resistor, right? But it's a ratio between the delta V over delta I in the log scale, right? This is also the recommended model from the vendor. And then we can estimate it, the voltage at peak current, right, equals to the voltage the system DC voltage, right, plus the voltage increase due to the current increase, right, from once voltage cross like only 2 kilovolts to when the current is like a few kiloamps, right, the peak current. So even though this is already the log scale, right, so that's how the MOV can clamp the voltages, but the peak fault current and also the continuous leakage current, right, they are missed by a few orders of magnitude. The peak current is in a few kiloamps, and the leakage current is in the range of 0.1 milliamp. That's the reason MOV actually cannot really clamp the voltage to that low as we want. Right? For example, this is MOVs that can continuously blocking 2150 volts, right, can meet the requirement, but its peak voltages will be 5,000 volts when carrying 2,000 amps only. Okay. So one way to do it is we just need to pick a devices that can handle this, right? 5 kilovolts, if it's peak, then we can pick devices can handle 6.5 kilovolts. The job is done. However, there is a strong motivation to reduce the peak voltage. The reason is lower the peak voltages means semiconductor devices with low voltage ratings can be used, right? And this can substantially increase the efficiency and the power densities of the breakers. And this is key to achieve NASA's very aggressive power density and efficiency target. This example, right, based on similar semiconductor technologies, same vendors, right, with the same mechanical dimensions. The only thing we change is the voltage rating from 0.3 to 4.5 to 6.5. And the rated current is decreased, and also the losses as carries 1 kiloamp also increase dramatically. So we definitely want to use the lower voltage devices, right, to do this. That means we have to reduce the peak voltages. So other than this kind of performance metrics difference, there are more choices from different vendors for lower voltage rating devices, right? Which means we have more freedoms to choose the devices. Okay, and by the way, we have to meet the insulation requirements at high altitude, and none of the devices is designed for that. So we have to screen it and to evaluate what's performance, right? And also, lower peak voltages also means easier insulation design at high altitude. Right? 6 kilovolts is much more challenging than like a 3 kilovolts design. So how to do this? How to reduce the peak voltages? We know that the peak voltages is determined by the MOV's clamping voltage and plus the transient voltage across the inductor. So if we talk in this part, one way to do it is reduce commutational loop inductance. With us, we do almost every day when design converters. Typically, that means a super compact mechanical layout, either bus bar or even laminated bus bars. Right? But however, this is quite challenging for this design, because super compact mechanical layout means much higher challenges for insulation at high altitude. Okay. And also it could mean weight penalties, right? Because laminated bus bars, not all the coppers are carrying current at its maximum current densities. So if we follow these parts, it's hard to meet the power densities requirement and also insulation requirement. Another way is we can reduce the device switching speed. For example, we have used devices with large turn-off resistors. This is preferred because the penalties of this is high switching losses, but this is nothing for solid-state circuit breaker applications. We only care about conduction losses. So as long as the device can handle that, this is almost free for the design. And also, once you slow down the switching speed, it can bring up a lot of design freedom for mechanical design, right? So I can play a lot of tricks in the mechanical designs to optimize the volumes and weight. And of course, right, if I can reduce the peak current, I can also reduce the DIDTs indirectly. That can also help. So if we're talking for the climate voltage of the MOV, right, this is the equations we can use to estimate the MOV's peak voltage. The DC bus voltage, we cannot change it. So either we either change the peak current, right, or change the current, leakage current, once in the steady state. So if you want to reduce the peak current, well, the easy way to do it is instead of using one MOVs, we can put parallel multiple MOVs, right? Because the system peak current is the same. The more MOVs you put in parallel, each MOVs will only share a small fraction of the current. For example, if we have one MOVs, right, 2000 amps is 5000 volts. If 10 MOVs in parallel, you can bring down to 4300 volts, right? It did go down. However, first is limited and also it's quite heavy, bulky, and complex. This MOV is 500 grams, 10 of them is 5 kilograms, and I only have 12 kilograms of budget per pole, right? And also, how can you collect so many MOVs in parallel? Probably you have to use the linear bus bar, right, to do this, because you also have to guarantee a good current sharing among the devices, right? It will make it complicated, bring insulation design challenges. And of course, if you can reduce the peak current directly, that'd be great. Or if you want to increase, right, the leakage current when the MOV is blocking VDC, DC link voltages, right, that can also help. However, we know that the MOV cannot do that, right, limited by the material. So we need to bring in help to help the MOV. One way to do it is we can bring additional switches, right, to cut MOV's leakage current, and after that, share the MOV's voltages in off state, right? For example, we can add a main contact here. So when the fault is cleared, right, we'll open the main contact to cut the leakage current flowing through the MOV. And this can also share the voltages and provide galvanic isolation, which is good. However, this is too heavy, right? Because this main contact needs to carry 1200 amps continuously, right? So you need a big chunk of copper to do that, and could be lossy. And also, most important, not commercially available. And this component needs to be available by 2023 to support LASA's flight test. And additionally, it requires active control to coordinate with the solid-state circuit breaker turn off actions, right? If you turn off too early, you are cutting the current, right? So it's not a contact, it's going to become a breaker, and we know it's very challenging and it's not doable, right? Or if you turn off too late, the MOV has already carried the high leakage current for too long, the MOV will be damaged. So this is really challenging to require active control. Another way to do it is to add an auxiliary switch in series with MOV, right? So this way is still cut the leakage current, right, of the MOV when it's blocking the VDC, and also these devices can also share the voltages with MOV. Okay, and also because the auxiliary switch doesn't carry the main current in operation, it doesn't generate heat, so there's no need for active cooling for the devices. The challenging part is the same, right? You have to be able to turn it on and off at the right time. For example, once I turn off the IGBTs, I want the devices to be turned on, so the current can be communicated to the MOV, right? And once MOV has decreased the current, clears the fault current, right? When it carries the current below 1 amp, I want the device to be able to cut the current at that moment, right? And this cannot be done actively. If it's actively too complicated, I'll end up bringing a high reliability of the component. Okay. So that's the key challenges. So I mentioned the peak current can also affect the MOV's the solid-state circuit breaker's performance, right? So if we want to reduce the peak current, first something we can do is we can reduce the threshold current, right? The one way we can do that is we can modify the gate drivers, right? Make sure that the gate driver can kick in and detect fault earlier, right? And also we can reduce response time. However, both of them will make it sensitive to system fault current, but at the same time, it's also sensitive to system transient and noises. Right? This, if we really push it, when reducing margins. And this can force trigger the breakers in the normal operation. We can also try to increase the system inductance, right? And make sure the current will increase slower. We can locate the breakers away from the source to leverage the existing inductance in the systems. But this also means additional safety risk for power system, right? Because whatever the cables in between, if the fault happens there, the breaker can be bypassed, okay? Or we can add additional current limiting inductors, right? For the ground level applications, probably it's okay, but for the aviation applications, this is just too heavy and noisy. Keep in mind, the target is 12 kilograms per pole. So the teams picked to reduce the IGBT's gate voltages and leverage IGBT saturation mode to do this. Right? Later on, you will see you have some efficient penalties, but very, very limited. Okay. So we reduce the gate voltages from IGBT from 15 volts typical to about 12 volts. So we can limit the fault current. So this is an example to show, this is test results for 3.3 kilovolts 1000 amp IGBT module. So if you can reduce the peak the gate voltages from 15 volts to 13, 12, 11, 10, right? As you can see, the fault current, the current that can flow through the IGBT actually saturated is limited by the IGBT, which means no matter how hard you try, the current flowing through IGBT is limited. Okay, the IGBT the terminal voltage across IGBTs will increase automatically to fight against it. Okay, so we pick 12 volts. So the peak current is about 2.5 to 3 times of the rated current. I think it is a reasonable value. So this is the proposed solid-state circuit breaker topology of the solutions. Right? So we have the MOVs, and so this is auxiliary switch we talk about. Right? They have the main switch is the thyristors, okay, SCR. And this is a few passive components. You can see a few diodes, resistors, and capacitors as in passive triggering circuits. Later on, I will explain how it works. But as you can see, the auxiliary switch is only comprised of reliable and mature thyristor-based devices without cooling requirement. The SCR, the main devices, can be turned on if there's a gate current injected into the gate, and it will be turned off automatically if the fault current, like current flowing MOVs and SCRs, is below is holding current levels. Okay. And we have the breakover diode. It's also kind of a thyristor-based devices. It behaves as high impedance, like open circuit, when the voltage is low. Right? When the voltage is high enough across it, then this will just be turned on automatically. Okay, become a low impedance. And because the SCRs, all the components in the current unidirectional asymmetric, so we have one group of these switches for each current directions, and we have this diode. Just make sure the current will not flow reversely. Okay. And also the IGBT, we have already reduced the gate voltage of IGBT. So you can see the fault current flowing through the system is already clamped. So this is operation principles. As you can see, when the fault happened, it's keep increasing, but then it will be limited by the IGBT's saturation current levels. And then the IGBT will turn off. The moment IGBT turn off, it will trigger the thyristors. The thyristors will be turned on, and the current will be commutated to the MOV, right? Then everything back to the classic solid-state circuit breakers, MOV will start clamping voltages and reduce the current to 0. Right? Once current is low enough, the thyristor will be turned off, and then the MOVs and also the thyristor, the breaker diode, they will starting to sharing the voltages in the standby mode. This is the basic idea. So this need to be details on how the circuit works. Right? First, IGBT turn on, it carries the current, and then we detect the fault. We turn off the IGBTs. If you turn off the IGBTs, right, the current, the voltages across the two IGBTs will start to rise up. Right? We may add some snubbers there, just make it softer and smoother. But these voltages will be shared by the thyristors and also the MOV. Right? So when the breakover diode voltage, shared voltage is high enough, the breakover diode will be turned on. And then all the voltage at this point will be applied to the MOV. So the MOV's leakage current will increase to a few amps, if designed right, a few amps rating. And this few amps current can be high enough to trigger the thyristor. and then the thyristor will be turned on, right? From T2, the thyristor will be turned on. Once the thyristor is turned on, then the current will just flow through the thyristors and flowing through the MOVs. Of course, the MOV will start to clamping the voltages. And after the current will start decreasing, after the current is reduced and it's reduced to almost zero, right? Then the VDC will be only applied to the MOVs, and the MOV will have some leakage current. As long as we pick the right MOVs and make sure the leakage current, right, once the MOV is blocking VDC, is below the holding current of the thyristors will be turned off laterally, right? Will be turned off laterally. So when thyristor is turned off laterally, the voltage sharing between the thyristors and also the MOVs will be determined by the static, like voltage divider resistance, right? We just pick the values here so we can control the voltage sharing across the SCR and also the MOV. And for easy design, we just keep it simple, half and half. So that's why we want to pick the MOVs and make sure MOVs can withstand, instead of 1 kilovolt or 2 kilovolts, can withstand 1 kilovolts continuously. Okay. As you can see, the whole passive circuit, trigger circuit is only one diode, one breakover diode, some resistor and capacitor. Actually, this is just a filter and some zeta diode, and also some additional passive components. So the size, the component number is very limited. It's purely passive and turn on, turn off automatically. And also the size and weight is very limited. So let's move on to the prototype design and test. So this is the module selected for this project, right? So as you can see, there are many options. They all have the standardized package, 190 millimeters by 140 millimeters. It's all commercial available. There's no single source, and it's interchangeable, right? We are evaluating different performance, okay? And most of the module level evaluations, actually, we are doing it for installation. Make sure they can handle the voltages and the PD3 at high altitude at different temperatures, right? But there's too much detail there, so I will not cover that in this presentation. So estimated efficiency, this is already considered 2-pole, so this is the total losses. Okay. So just 2 examples. One is 2000 amp devices, one is 1500 amp devices. As you can see, 2000 amp devices is the latest generation of IGBTs, so it has lower losses and high efficiency. Okay, so these two are for the 2000 amps. This is for the 1500 amp devices. And these 2 curves showing the efficiency difference when you apply 15 volts and 12 volts, right? There is some difference, but however, the difference is marginal. Okay. But the good thing is, even with 1500 amp devices with 12 volts, right, it can still meet the 99.5% efficiency target. And by the way, this is the efficiency based on the datasheet values at 150C, right? But during the regular operations, the devices, the junction temperatures will be lower than 150C for sure, right? Which means the efficiency will go higher. So the actual efficiency we're expecting is higher than 99.5%. Mechanical layout, right? So this is 2 devices. We have 2 IGBTs per pole, ID series. And this is just a regular bus bar. There's no lamination at all, right? With the gate drive. And this is the MOVs, and this is the thyristors, which actually this is we take the 2-in-1 SCR, right? Because SCR is very good at handling surge current, and it's very compact. And this is just a passive trigger circuits. This is already for 2 thyristors, okay? And in this design right now, we're still using some slappers, some regular RC slappers, again, to try to slow down the DVDTs. It makes everything softer. So we're already cutting a high current. So we want everything as soft as possible. So this is dimensions of the boxes. The total volume is about 0.88 cubic feet, or the 0.025 cubic meter. So this is only the body, the chassis, right? So as you can see, there's some additional bus bars extruded outside the boxes for the external cable connections. So that is not included. The weight breakdown. So we have already done the design to bolts and nuts. So this total weight about 40 pounds. This is already included everything. As you can see, the electric component, mainly the modules, is about 1/3 of the weight. And the majority of the weight is still coming from the mechanical enclosures, the heat sink, and also the bus bar. We may need to add additional insulation materials later on for meet the insulation requirement. This has not been included. And we may need additional mechanical support for the bus bars. Right? That so far has not been included. So with these designs, the power density is about 96 megawatt per cubic meters, and or 133 kilowatts per kilogram. Right. So with this, I think we still have some margins to meet the 100 kilowatt per kilogram target. So this is the solution test setup, like a benchtop testing right now. So it's nothing fancy. We have a capacitor bank. We have the air core inductors can emulate the different inductor values. Right. We have the hot plate. We can control the IGBT's temperature. So when we do it, we just pre-charge the capacitors, then turn on the devices and create a short circuit, right? And to cut the fault current. So this is the test setup where we're doing right now with the right devices, the bus bars, and almost the same layout as in the mechanical designs, MOVs, the slabbers, the thyristors, and also the passive trigger circuits. So this is the test results, right? 2000 volt DC with 12 volt gated voltages and 50 microhenry inductors. Okay, so I have done a series test, but here I only show the two extreme case, 50 micro and almost 0 microhenry. 12 volts gated voltages, right? At the beginning, the MOV and SCR voltages are almost the same. As I said, it's shared by the steady state, the resistors, right? Voltage divider. And we turn on the devices, then the current will start to increase because you have fairly large inductance. The current is only 40 amps per microsecond, right? Rising up. And it will trigger the DC protections. Right? And then after delay time, IGBT peak current is about 4,000 amps. And system peak current is about 4,100 amps, right? There's some additional current flowing through the slabber. And the SCR is triggered on time and kicking the MOVs. And the peak voltages in this case is about 2766 volts, which is way below the 3.3 kilovolts IGBT's voltage rating. And after that, the fault is just cleared with about 300 microseconds. Okay. The measured energy absorbed by MOV is about 1 kilojoule. And again, this is already the worst case. We are using one single pole to clear the fault. Right? This is only a zoom in the waveforms of this the previous test result. Oh, sorry. Zoom in the waveforms here, show more details what happened during switching. Right? As you can see around here, the IGBT started to turn off. The IGBT current will start to decrease, and at these times, the MOV has not been kicking. So most of the current will flow through the slabber, but the voltages across IGBT will start to increase. Right? This is the green curve starting to increase. And these voltages will be shared by the MOV as SCR. Once the SCR voltages increase, achieve a certain point here around like 1200 volts, we take the breakover diode voltage ratings at around 1200 volts. The breakover diode will turn on. So once the breakover turn on, during this process, the MOV's voltage will start to increase. The highest MOV voltage is the highest leakage current. This current will be high enough to turn on the SCR. Right? So SCR after this point will be turned on and remain on. Right? Since still have high current, the MOV current, the same current will flow through the SCR. The SCR will keep turning on and keep on, and then the fault current, as you see, the fault current will start to decrease. Right? When the current is reduced low enough, the SCR voltages, SCR will be turned off. Then as the SCR voltages and MOV voltages will kind of merge together, right, back to this state. This is the test results. So when we have 2000 volt, 12 volts, 12 volt gate, and also 0.3 microhenry. So we twisted the cables, make sure this is the lowest induction we can get. This is only from the external, right? The circuit breaker itself also has a few hundred nanohenry inductors. So clearly, this case, the current increasing pretty fast. It's about 2.5 kiloamp per microsecond. Okay. However, because of IGBT saturated, right, so the current actually is clamped to 5.4 kiloamp. As you can see, it's clamped. If it's not clamping, the current will keep increasing, and probably when we really start to cut it, the current is already definitely more than 10 kiloamp, which will make it super difficult to cut it. But now it's limited to about 5.4 kiloamp. Okay, as you can see, when the current is increasing, the IGBT voltages will increase automatically, try to reduce the current, right? Reduce the current increase. The gate voltage is removed somewhere here, right? You can see the IGBT voltage keep increasing, try to limit the fault current automatically. And because of this, the IGBT, the peak voltages during switching is only 2800 volts, which is still below the 3.3 kilovolts voltage rating. In this case, the e-MOV is activated when the voltage across about 1151 volts. However, as you can see, in this case, MOV doesn't help too much, right? Because the induction is too low, and we did limit the fault current. The fault current is also kind of low. So the energies stored in the systems is kind of low, right? So this energies, most of the energy actually is absorbed simply by the flapper, right? Because we limit the fault current. If we keep increasing the external inductance around like 1 microhenries, we do see that both this is triggered and also the MOV is kicking to help them absorb the energies, just like in the regular case. Okay, so you can see the energy is almost nothing; it's only like 70 joule. So we did hit the IGBT to see how the performance will change. But as expected, the higher the temperatures, the higher the VCEs, and the lower the saturation current levels, which is all good to help improve the performance of solid-state circuit breakers. Right? These examples here, this is room temperatures, this is the 100 degrees junction temperatures. So peak current is reduced from 5,500 amps, right, to about 4,400 amps because the junction increased. So this will be closer to a real case when the devices is carrying the current, right, load current. And because lower current, then the peak voltage is also reduced to about 2650 volts from 2830 volts. And we see the same trend at high inductance. Right? At high inductance, the VC is higher, so we can detect the fault current earlier. Then the peak current is reduced, and peak voltage is also reduced at high temperature. Okay, I think I finished it within about 40 minutes. So we can see this 2 kilovolts, 1.2 kiloamp solid-state circuit breakers is designed with the e-MOVs and also reduced gate voltages. The proposed solutions can meet the power rating, density, and efficiency target. The experimental results verify design, and the fully assembled solid-state circuit breakers will be tested with the whole power chain in the emulated high altitude environment in 2023. So that's the reasons why we have to pick a mature technology and make sure everything is as simple as possible, right? Because this one really need to be tested again in the power chain in Glenn Research Centers in Cleveland, right? There is electric aircraft test bed, okay, and after that, this device is maybe tested in the flight system, in the flight test. Okay, I think that's it for today's presentations. And any questions, welcome.
Thank you, Dr. Zhang, for a wonderful talk. I'm sure the audience will concur with me that this webinar has been very informative. We'll now go to the question and answer part of the webinar. Okay, let me start off with a couple of questions that were already posted here. The first question is from Chase Sun. Dr. Zhang, this may not be your topic, but one of the major challenges for electric power airplane is the weight of the battery. How much battery capacity will be required for longer distance air travel? What is the weight of the battery? Is NPS looking into this issue as well?
Okay, so let me go back to the previous one. So there are many architectures for the hybrid electrical propulsions, but probably battery is so far is not an option. Okay, that's why NASA is focused on this turbo electric aircraft. This is a single L turbo electric aircraft with the after boundary layer propulsors. As you can see, there is no batteries. The key ideas is just move the powers from the engines to the tail cone fan to achieve a fuel burn reductions. This is about, based on studies, about 8%. Okay, so this is definitely not using the batteries. Batteries more for small aircraft But for small aircraft, it's a different stories, as you can see. But here for these studies, we're talking about megawatt powers. It's not involving batteries.
Okay, so moving on to the next question. This is from Dave. Won't the MOV have finite life? Is there consideration to monitor the number of breakover events?
Yeah, so that's a good question. MOVs also have limited lifetime, and the vendor typically give you a chart, right? So what kind of energy? It depends on what's the total energies each time the MOV is absorbing, and also the peak current, and also durations of current, right? The vendor will provide the chart for that. So eventually, if this one will really become a product, then we have to keep monitoring how many times the MOV has been used, and each time how many energies is absorbed, right? But as you can see for this case, in the worst case, 50 microhenries and 4 kiloamps, right? This is really the worst case. If you have two MOVs, it's working already. It's working there. Each of them is only 300 joule, right? It's less than 10% of the total power ratings for in this design, specific design. Okay, so if you use a circuit breaker to cut the regular current, let's say the 1 kiloamp, not full current, just 1 kiloamp, the energy is even lower. So we have done some preliminary studies and didn't identify the huge risk there. So it's doable.
Okay, all right, thank you. So this question is from Jeff Niles. I think it is very heavyweight. What are the comparison weights for other solutions, if there are other solutions?
I think this is all the questions for NASA. So we get this back from NASA. NASA believes there's no solutions at this point can meet the requirement. And I think based on the feedback from NASA, the power density or weight we have achieved is already exceeds their expectation.
Okay, yeah, thank you so much for that. The next question is from Miaojin Wang. Do you use liquid cooling?
Yes, liquid cooling is required and provided by NASA. And not only the solid-state circuit breakers, it's also as the power converters and also the motors will also be liquid cooled to achieve a high power density.
Okay, all right, thank you for the answer. There are a couple of questions from Mikhail. What are consequences of the MOV failure in the proposed circuit?
If MOV failed, then the solid-state circuit breakers will not be able to continue functioning, right?
Right. Okay.
So you will have additional. So we are talking with NASA. So for the solid-state circuit breaker designs, we just want to keep it as simple as possible, of course with margins, but as simple as possible, right? So if we want to consider the failures of the agent component for reliability, I mean, just like any other component, then we have to add additional redundancy at the system levels, not at the component levels. Right? So components, we just want to make it as simple as possible to improve the efficiency and the reliability.
Right. Okay. Following up on that, did you consider alternatives to MOVs such as DTTs or even RCD snubbers?
The MOV so far is still the most efficient way to absorb energies. So it's so compact and also can absorb a lot of energies. So at this point, we're only considering MOV, and the slubbers is only as you can see, the slubber cannot really absorb too much energies, right? Energy density wise, it's not comparable with MOV, not even close. So the slubbers we put there is just to slow down the DVDT and DIDT. That's it. Yeah. We're not relying on the slubbers to really absorb the energy.
Yeah, I think those were the questions. If there are any other questions from the audience, please feel free to either put it in chat or raise your hand and you can ask your questions directly to Dr. Zhang. Brian, please go ahead and ask your question.
All right, thank you, Sean, and thank you, Dr. Zhang. A great presentation. It's really fascinating, especially to see what you're doing with the density there. So speaking of the density, I'm curious, what do you see in terms of, not from the, energy storage and commutating components, but kind of from the rest from a materials perspective, what do you see as kind of the key enabler to make a a significant difference in the, in the swap solution total.
Maybe for the futures, how we can, how the new material can help to improve the performance. Is that your question?
Yeah, how will you continue to, improve this and make it lighter? Yeah.
Sure. Well, one thing is, I would say, the definite devices is the key. Right here, you can see there are two key component. Component. One is semiconductor devices. The other one is e-MOV. Right. So semiconductor devices, again, we have to deliver this by 2023. So I can share one chart with you guys. So that's why we have to use all the mature technologies. Anything commercial off the shelf, we can use it. Otherwise, it just doesn't meet the schedule. So, for example, silicon carbide devices, right? We look at the silicon carbide devices, okay? Oh, sorry. So this is, again, there's no commercial off the shelf 3.3 kilovolts, like 1500 amps, 12,000 amps, single device, right? Silicon IGBT MOSFET. There's no such component. So we can find this component from Hitachi, right? This is 3.3 kilovolts, 800 amps, dual silicon carbide MOSFETs. So if we can say we can magically convince Hitachi to repackage this, right? Use the same dies, put them as a single devices, right? As basically we claim it has a 1600 amp single devices, right? So then we compare that. This is a green curve. Compare that with 2000 amps and 1500 amps IGBT. You can clearly see that the benefit, this is with 15 volts gate voltages, right? So efficiency is much higher at light load for sure, as we expected. And efficiency is comparable, right, at the heavy current, okay? So this is silicon carbide devices. But however, if you look closer, this modules is only 100 millimeters by 140 millimeters. So the IGBT is 190 millimeters. So this is roughly half the size, right? So if you can further put two of these modules in parallel, right? So this will become the blue curve is efficiencies, if you for a fair comparison for the same mechanical dimensions. Then you can see the silicon carbide definitely can further increase the performance, right? Either the efficiencies or the power densities, right? If you reduce the mechanical dimension, everything become lighter, right? So this is the potential, but there are some challenges, right? For example, the reasons they can achieve this super high current density is because there's no separate diode, right? They are using the body diode to temporarily carry the current during the daytime. Okay, that may work for converter applications because we know the daytime can control it to be less than 1 microsecond. However, for breaker applications, right, the current may be very high, and the body diode capability of body diode to carry a few times of rated current for a few microseconds. This definitely need to be verified, right? So the reason is because IGBT doesn't have a body diode, right? So we have to have 50% of the size, the die size, as IGBT to carry the selective current, right? So that's the reasons why IGBT has a lower current densities compared with silicon carbide, at least for now, based on current technologies. So if we can develop IGBT, the bidirectional conducting or bidirectional blocking, that can also help us to improve power densities of the applications. And also, silicon carbide devices doesn't have the good saturation or current limiting capability of silicon IGBT. So this is also another issues. So if we did have these silicon carbide devices, so how can we achieve the same current limiting capabilities, right, without using additional inductor? Because the inductors are quite heavy, okay? And of course, the e-MOV, if we can get new e-MOV materials, right, as I said, to further flat that VI curve, right, definitely that will also help to improve the power density and also the efficiency.
All right.
Does that answer your question, Brent?
Yes, sir. Yeah, yeah, I understand your time limited, but yeah, I was expecting something in the wide band gap arena, and then maybe I just wasn't sure if, well, I guess thermally, I guess I was thinking too, as much as you're mitigating so many of your losses, that you get to a point where you can save in the thermal solution as well.
Yeah.
But, yeah, fascinating work. Thank you.
Yeah, but that takes time. Doesn't happen before 2023.
Of course.
Right.
Well, I hope you get more funding.
All right. I think we have time for one more question if there's any. If not, then I think we can close the webinar. Before closing the webinar, Dr. Zhang, if I may share my screen.
Oh, sure. Yeah.
Just to, yeah.
Thank you.
Yeah. So yeah, thank you, Dr. Zhang, for the wonderful seminar. It was very informative, and I'm sure the audience found it very useful. And I urge the audience to contact Dr. Zhang for any other questions. As Brian already mentioned in the chat, we'll be uploading the PDF slides and the recording on our archive section, so the audience can go through it. And I would also like to thank our IEEE co-sponsors, the Santa Clara Valley PES chapter, the Milwaukee Pulse chapter, SCV Reliability chapter, PI Square Austin chapter, the SCV PSES, and the Oregon PES chapters for all the support. I would like to thank Dr. Zhang for your time for presenting this. And I would also like to thank all the audience for attending this webinar. Hope you found this useful. And one last thing before I let go is, so this is the talk schedule, as I mentioned earlier. We have a bunch of talks coming up through this year, and we'll be sending out more information as we get closer to the talks, but please feel free to register for those if you're interested. All right, with that, I think we can conclude the webinar. Thank you all.
Thank you.
Thank you.